from the colleagues
We're
in
going to
Stuttgart.
start with the paper
from the colleagues in Stuttgart. I'm happy to see their contribution at the 7th CIRPe Global Web Conference. The main author is Carsten Ellwein, and the other co-authors are Sascha Neff and Professor Alexander Verl, the head of the Institute for Control Engineering in Stuttgart. The paper is entitled Cloud Manufacturing, an Automated Literature Review, and I'm keen to see the method and the infrastructure the colleagues in Stuttgart used to do their research. Please.
Hello, my name is Sascha Neff and I come from the University of Stuttgart. The paper I would like to present to you is entitled Cloud Manufacturing, an Automated Literature Review. My colleagues who are also involved in the design of the paper are Carsten Ellwein and Alexander Verl. The structure of my presentation is as follows. First, I would like to introduce you to the topic by explaining why we are conducting a literature review on cloud manufacturing and why in an automated manner. Then, I will present the methodology of the automated literature review and after that its findings. At the end, I have prepared a conclusion which contains a summary and an outlook. Cloud manufacturing is defined as a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable manufacturing resources, for example manufacturing software tools, manufacturing equipment, and manufacturing capabilities that can be rapidly provisioned and released with minimal management effort for service provider interaction. So, in the context of Industry 4.0 and globalization, the idea of transferring cloud computing to industry is called cloud manufacturing. With cloud manufacturing, we have on the one hand manufacturing as a service and on the other hand collaboration throughout companies. The paradigm cloud manufacturing was defined for the first time in 2010. Since then, the number of literature on this topic has increased tremendously from year to year. Regarding Google Scholar, the number of literature results increased by over 16% last year. At this moment, Google Scholar contains in total over 6,800 literature results on cloud manufacturing. The challenge that now exists is to make this large amount of literature controllable. So what's the content of this paper? In order to make the large amount of literature on cloud manufacturing controllable, we conduct a largely automated literature review. The goal is to identify the different research fields of cloud manufacturing and also show their development trends so that you can see which research fields are important at the moment and which have been completed. For this purpose, a statistical evaluation of literature metadata is carried out in an automated manner. This provides results that are completely replicable. Now, I show you the methodology of the automated literature review. First of all, the framework conditions must be defined. The search for the term cloud manufacturing in Google Scholar with literature from 2018 shows that the most frequent literature results come from the databases of IEEE, Elsevier, and Springer. For this reason, these three databases are used for data collection. The search term used for the databases is defined as cloud manufacturing or manufacturing cloud. The literature metadata from the databases in form of CSV and text files are extracted and processed by using scripts and web crawlers in Python. The web crawlers are required to obtain specific metadata of literature which is not provided in the database files. So, one part of the basic approach is the statistical evaluation of literature. For this purpose, simple statistics such as the literature distribution per database, year of publication and affiliation country are created. The other part of the basic approach is the evaluation of keywords, which is not that simple and whose procedure we now take a closer look at. The first step is to read in all keywords from the databases by use of Python. During this process, adjustments are made to the keywords to keep them in the same format. This includes the exclusive use of lowercase letters, hyphens, slashes and underscores are replaced by spaces, and all other characters are deleted. Often keywords are only indicated by their abbreviations. To take this into account and to identify them, the Wikipedia's application programming interface is used. Now, to summarize all keywords, we use two methods of natural language processing. First, we have the stemming method, which reduces a word to its root. The advantage of this method is that no distinction is made between the types of words. The disadvantage is that the word root can exist in a form which no longer represents a meaningful word. Then we have the lemmatization method. This method reduces a word to its basic form, so it's ensured that the word still has a useful meaning. However, a differentiation of the word in relation to the word type is maintained. So what we did is that we combined the two methods to a hybrid version. Here on the right side of the slide, I have shown you the algorithm. At the beginning, we stem the keywords to its word roots. The algorithm then checks whether the roots are identical. If this is the case, the lemmatization method is used and the keywords are merged. No changes are made in case of different word roots. So with this algorithm, we combined the advantages of both methods. Now, in order to cluster the keywords, we use a method from machine learning called latent semantic indexing. This method is based on the principle that words used in the same context have similar meanings. So we created an extended list that contains all keywords, including the hyperlinks from Wikipedia as a context. This list is then converted into a mathematical corpus which can be compared with all keywords. So this automatically generates a semantic similarity measure between the keywords, and similar keywords are assigned in the same cluster. In total, we analyzed about 1,100 literature results. On average, about 5 keywords are given per literature result. From almost 500 summarized keywords, 29 clusters are automatically formed. But after a closer look on these clusters, manual adjustments were needed to bring the clusters into a final form. Therefore, clusters like 3D printing and additive manufacturing, as well as production and manufacturing, are combined. Furthermore, are keywords defined as clusters only if the number of occurrences exceeds 0.5% of all keyword occurrences. The manual optimization then results in a total of 12 clusters, which I will show you later. As a summary of the methodology, I want to give you a general overview. For the data collection, we use the databases from IEEE, Elsevier and Springer. First, we do a simple statistical evaluation of literature. Therefore, we create statistics of the literature distribution per database and year of publication. In order to get the affiliation country for each literature, we need web crawlers. After that, we also can create statistics of the literature distribution per affiliation country. The second part of the methodology is the evaluation of keywords. But before doing this, we also need a web crawler to obtain the keywords from Springer because they are not indicated in the database files. So now we can scan all keywords and summarize them by means of the stemming lemmatization hybrid algorithm. And finally, we can cluster the keywords by using latent semantic indexing. After that, we need manual adjustments, and so we can visualize the final clusters with their development trends. Let me show you now the findings of the automated literature review. As I mentioned before, a total of about 1,100 literature results from the databases IEEE, Elsevier and Springer are considered. Concerning the statistical evaluation of literature, I will show you now the statistics of the literature distribution per database, per year of publication, and per affiliation country. On the right side of the slide, you see the statistics of the literature distribution per database. With almost 44%, the Springer database provides the largest contribution of literature on cloud manufacturing, followed by the database Elsevier with 39%. With a contribution of about 17%, the IEEE database publishes comparatively less literature on cloud manufacturing. Now, let's take a look at the statistics of the literature distribution per year of publication and per affiliation country. In 2010, literature on cloud manufacturing was published for the first time. Since then, the number of publications has increased from year to year. The development represents an exponential distribution. Most of the literature results are published in China, as we can see in the statistics of literature distribution per affiliation country. The United States comes in second, clearly behind China. The United States is followed by Germany and the United Kingdom. Sweden ranks fifth, followed by Taiwan, Italy, India, New Zealand and Greece. The number of literature results from other countries is summarized. With more than 200 literature results and 41 countries, this part represents also a considerable contribution to cloud manufacturing. Let's talk about the findings concerning the evaluation of keywords. We have identified 12 clusters in total. In order to visualize the development trends, for each cluster we use bubble charts, as you can see on the right side of the slide. The larger the bubble, the more often the keyword in this cluster occurred. On this slide I want to show you the clusters with an increasing development trend. Therefore, the clusters Industry 4.0 and Internet of Things are strongly represented. Also the clusters Big Data, Cyber-Physical System, Smart Factory and 3D printing show an increasing development trend and are also growing in importance. Now I want to show you the clusters with a constant or decreasing development trend. Such development trends indicate clusters with a constant or decreasing importance. These clusters are cloud computing, ontology, service management, industrial robot, production, and digital manufacturing. In these research fields, for example, sufficient research has already been conducted. The data of all evaluated literature, including their assignment to the clusters, are available online in GitHub. The corresponding link can be found in the paper. The conclusion. Let me give you a short summary. The number of research papers on cloud manufacturing has increased tremendously in recent years and seems to continue to increase. Most of the evaluated research papers are published in China, followed far behind by the United States and Germany. Regarding the evaluation of keywords, important clusters and current research focuses are Industry 4.0, Internet of Things, Big Data, Cyber-Physical System, Smart Factory and 3D printing. The procedure of this literature review can be completely replicated. However, the latent semantic indexing algorithm for cluster formation does not yet provide optimal results. Manual adjustments are necessary to bring the clusters into a final form. So, the improvements regarding this paper can be divided into three groups. Tooling is about simplifying usage through a graphical user interface, for example, and channelizing the toolchain to include other search terms and research fields. Algorithm is about recognizing false positives and reworking the clustering methodology to avoid manual adjustments. Databases means to exploit further databases and also to create further statistics of literature metadata, for example, the statistics of literature distribution per author. Thank you for your interest so far. If you have any further questions concerning this presentation following CIRPe, please don't hesitate to ask me in the discussion afterwards or contact my colleague. Thank you.
Thank you, Sascha, Neff, for doing this presentation, for submitting the paper together with your colleagues. What I was really positively surprised was that when you see the paper, there is a link in the paper where you can access the data which lies behind that kind of literature review, and I'd like to refer you to this kind of data. We're now having time to discuss some questions with Sascha Neff. We're trying to get him live here now. Hello, Mr. Neff, can you hear us? Hello, thank you. Very nice to see you online here in that paper presentation about the automated literature about cloud manufacturing. From my own experience, I know that these large number of papers, automated literature review may get distracted by misclustering and so on. Can you comment on the use or the benefit of manual reconfiguration or manual help for the algorithm?
Of course. Right now, all of the Python scripts have to be executed manually, one by one. And I have to say the combination of all Python scripts in the form of a framework would come very close to a fully automated literature research. And right now, we also need manual adjustments after the algorithm has checked all keywords. And it's very complicated to form those clusters automatically and nearly impossible to do that in a perfect way. For example, if you have 3D printing and additive manufacturing, it's nearly the same, but you have to put them in the same cluster, and also production and manufacturing has to be in the same cluster, and it's difficult to form that in an automated manner. And so what we did in the end, to perform good results, we did manual adjustments to cluster the keywords and to summarize them one more.
Thanks for the answer. I also wondered how does that system scale? So how much more complex, how much more effort does your system need when the number of papers or the number of databases that you crawl through increases? What do you think is a practical limitation for that?
It's difficult to define this limit. Therefore, we have to test all the databases as well as all the themes. Right now, the Python scripts have to be executed one by one, and one Python script also, for example, the web crawlers, they need a lot of time, several minutes to go through. And you have to test it with more databases and with more themes and with more literature. And I think there's quite some space to get there. But I have to say, we need a framework, for example, also with a graphical user interface, where the user can search a term and just have to click to get results automatically.
Okay, so it's also about the front end to make that more convenient to use.
Yes.
Okay. One last quick question. In your results, you have found out that the publication numbers from China are way more than they are in any other of the considered locations. Can you comment on that?
Yes, the fact that China is the leading force of research in cloud manufacturing is reasonable, in my opinion, since China in particular could benefit greatly from a successful implementation. China's economy is dominated by manufacturing companies with huge production factories that live on business with other companies. And large production and sales volumes are needed to keep up with the high pressure on prices. And China's economy has been characterized by a strong boom in recent years, and not least to these manufacturing-intensive companies.
Okay. Thanks for sharing these insights with us. Thanks for joining the conference and the live question and answer, Sascha Neff.
No problem. Thank you for being here.
Goodbye.
Bye.
So this was the paper presentation and live question and answer for Cloud Manufacturing and Automated Literature Review, authored by Carsten Ellwein, Sascha Neff and Alexander Verl, affiliated to the University of Stuttgart.